Here we're going to talk about static charge and current. Some of this you've seen before, probably in grade 9. Some of it might seem a little new to you. First, a little bit of history. You might recognize this character. If you're a fan of American history, that's Ben Franklin, doing his famous experiment with the kite and the key, and a little bit of lightning. But the ancient Greeks actually knew something about static charge, because they knew that it could be accumulated by rubbing fur on various substances like amber. Amber is that hard yellow substance that can form in certain kinds of trees. Then the amber would have a charge and it could attract small light objects like feathers. You might remember amber if you've seen Jurassic Park. Amber was the stuff that the mosquito was found in. Whence they got the DNA to generate their dinosaurs. They also found that if you rub these materials together long enough, then they could get sparks to jump from them. Then eventually in the 1600s, scientists returned to the subject of electricity and they invented the word electricus from this word, which is a Greek word. I'm not going to try and pronounce it. Well, okay, I'll give it a shot. Electron. Now we spell it with a C instead of the K. It's actually the Greek word for amber. Garrick invented the first electrostatic generator in the 17th century as well, and found that like charges repel. So positives repel positives, and negatives repel negatives. Boyle used a generator and Garrick's other invention, an air pump, and found that electric attraction and repulsion can even act across a vacuum. So it didn't matter if there was air in the room or not. Then in 1729, Gray classified materials as either conductors or insulators. You'll probably remember those terms from grade 9. Conductors can carry charge or allow charge to pass through them very easily. Insulators, however, do not allow charge to move through them easily. Here we see a diagram showing us various materials and how good they are at conducting electricity. So the conductors, you'll notice, silver over here, copper, aluminum, iron, mercury, etc. You'll notice that the conductors, most of the conductors have something in common. You probably notice that they're all metals. The insulators, on the other hand, way down at this end, rubber, glass, wood, dry air, those, not surprisingly, are non-metals. Copper is such a good conductor that we use it for most of our electric circuits. Aluminum used to be used for electric circuits, but it can tend to cause fire, so we only use it outdoors now. But what is electricity? Well, going back to our old friend from the States, Ben Franklin, he argued in favor of a theory called the one fluid theory. There he is again. And that said, that electricity was a type of fluid that was present in all matter, and an excess of it resulted in positive charge, and a deficit of it resulted in negative charge. Well, I'm not too worried about the robot apocalypse just yet. I'll give it a few years. Actually, positive charge results from not an excess of electrical fluid, but a deficit of electrons. So if an object is missing electrons, it will become positively charged. The negatively charged particles on the outside of the atoms can be easily removed from some materials. You'll remember this picture from grade 9 as well. If we remove the electron, then the material can become positive. Or in this case, the atom becomes positive. If you remove a lot of electrons, then the object will have a strong positive charge. We can charge things by friction, by rubbing them together, because some materials have a stronger electron affinity than other materials. You might remember this from the electrostatic series in grade 9 as well. So for example, a rubber rod will acquire electrons. That means it gets a negative charge when it's rubbed with fur. It means that the rubber has a greater electron affinity than the fur does. The electrons will be transferred from the fur to the rubber. Now, any charge that's acquired by friction can be conducted to another object that has a smaller, opposite, or neutral charge. You might be familiar with this as well. You walk across the carpet, and you go to touch the doorknob, and you feel a zap as the charge is transferred. You can also do it to people. They might be annoyed. So why? Why does this happen? Well, electrons flow from a charged object to a neutral object because they want to be as far away from each other as possible. Remember that like charges repel each other, and electrons all have the same charge, so they're like charges. So they're pushing each other away. Unlike charges, like negative electrons and positive nuclei, attract each other. The charge on a single electron has actually been measured. It was measured by Robert Millikan back in the early 1900s. Charge, written usually as Q, big or small, doesn't really matter, is measured in coulombs, named after Charles Coulomb, a French scientist who did a lot of work with electricity. So Millikan measured the charge on a single electron, and the magnitude of that charge we write as lowercase e. So the charge on the electron was found to be 1.602 times 10 to the minus 19 coulombs, and it's negative. Remember, electrons are negative. If we measure the rate at which the charge moves past a certain point, then we're measuring current. And we use the capital letter I to represent current. We can determine current if we know the amount of charge that's passed a certain point, say in a circuit, in a given amount of time, with this equation. Current is equal to charge divided by time. And charge is measured in amperes, named after André Ampère, this fellow, another French scientist who did lots of work with electricity. 1 ampere is equivalent to 1 coulomb per second. Let's try an example. We've got a lamp that uses a 7-watt bulb, and it draws 0.060 amperes of current. How much charge must pass through the bulb in 8 hours? Well, let's try our new current equation, charge divided by time, but we'll rearrange it because we need to get charge by itself. So charge is equal to the current multiplied by the time. You'll notice that I've converted the time to seconds because 1 ampere is equal to a coulomb per second. And we get 1.7 times 10 to the 3 coulombs, or 1,700 coulombs of charge is passed through the bulb in 8 hours. If we get electrons to move consistently, then we get a current that can be used. There are 2 different kinds of current that we use, DC and AC. You've probably heard of those before as well. Electrons will move from a negative terminal to a positive terminal. So as they're flowing through the circuit, here's our positive, here's our negative, and the electrons are moving this way. Now that's not always the way that we define current, but it's the way scientists usually think of it, because we like to think of the electrons moving and carrying energy. This is the simplest kind of current, direct current. That's the kind you get from a battery. It means that the direction of the current flow is always the same. We also have current that will change direction. In North America, alternating current, or AC, changes direction 120 times every second. That's because it's generated at a frequency of 60 Hertz. So it alternates. It goes back and forth over time. And there are some important reasons for that, which we'll talk about later. It provides for some great efficiency and some conveniences as well. Now, as I said, we don't always define current as the movement of electrons from negative to positive. We also have what's called conventional current flow, which is defined as the opposite kind of current, where the current goes from positive to negative. Regardless of the type of current you're talking about or the definition you use, electrons are flowing because they're given energy by the battery, measured in joules. In the case of the photograph we just saw, the energy was provided by that battery, but it could be provided by a generator or some other device, like a solar panel. The energy per unit charge is called potential difference. That's often called voltage. I'm sure you've heard that term before. We can calculate voltage by taking the energy provided and dividing by the charge that's present. So voltage equals energy divided by charge, which looks like that. And since energy is measured in joules and charge is measured in coulombs, that means 1 volt is equivalent to 1 joule per coulomb. Let's try another example. What amount of energy does it take to move a charge of 2 millicoulombs across a potential difference of 1.5 volts? Well, we'll try our new voltage equation, but we'll rearrange it because we need to get energy by itself. So energy equals the voltage times the charge. So our voltage is 1.5 volts, charge is 0.002 coulombs. Notice I've converted from millicoulombs that were given in the question. So we get 0.003 joules. That's not very much energy. All right. Next, we'll try a lab inquiry activity to see if we can generate some charge and current. I hope you don't find it shocking.